Let's consider this reaction between iron 3 plus and hydrogen thiocyanate to form the iron thiocyanate complex and H plus, all in aqueous solution. We can see that the equilibrium constant expression for this reaction would be iron thiocyanate concentration times H plus concentration divided by iron 3 plus concentration and the hydrogen thiocyanate concentration. If this reaction is in equilibrium, then at room temperature, then this equilibrium constant will equal about 60. So in other words, the ratio of reactant product concentrations to reactant concentrations will be 60 when we are at equilibrium. Let's imagine that we have this reaction at equilibrium. And so we have a concentration of all the different reactants and products such that the ratio is equal to 60. What would happen if we added, so let's imagine adding H plus to this reaction. So just make the solution more acidic by adding H plus. If we do that, then we can see that we originally had equilibrium concentrations. If we add H plus, then we make this numerator too big. And so this ratio will no longer equal 60 because we've added something to the numerator. And so what will happen is we will end up with a reaction quotient, because we're no longer at equilibrium, that is greater than 60 because we've included some concentration that numerically is in the numerator. So if we're no longer at equilibrium and we want to get back to equilibrium, then we're going to need to do something to make this Q value decrease, get back down to 60. So the only way to do that is to reduce the number of reactants and reduce the number of products and make more reactants. So in other words, we need to use up the products and make reactants, and we need the reaction to go in the reverse direction. So what will happen when we add the H plus is that the reaction will proceed in reverse to use up the H plus that we put in. And when we get back to equilibrium, we will end up again with a ratio that is equal to 60. On the other hand, if we remove H plus from solution, so if we had a way of removing the H plus from solution, we would end up with a Q value that would be less than 60, because in this case, we've removed H plus from the solution, so this concentration is smaller than it needs to be for equilibrium. Everything else is in its equilibrium concentration, and this is too small, and so our ratio is going to be less than 60. So to get back to equilibrium, we're going to need to do something to increase the value of Q back up to 60. And so the only way to do that is to make more products and use up reactants. And so the reaction is going to shift toward the product side, and we are going to have the reaction proceed forward until we get back to a ratio of 60. So you can see that whatever we do in terms of adding or removing reactants or products from this reaction, the reaction is going to proceed in the direction to counter that change. So if I add H plus, the reaction is going to proceed to use it up. If I remove H plus, the reaction is going to proceed to make more H plus. Likewise, if I added HSCN, the reaction would move in a direction to use up the extra HSCN. If I remove HSCN when I'm at equilibrium, then the reaction is going to move in a direction to make more HSCN to replace what I took out. And so the general principle here is that the reaction will proceed in a direction to counter the effect of whatever I have done to the concentrations. And that is the basic idea of LeChatelier's principle. Reaction proceeds back to equilibrium by countering any external change that we have made.